the what you need to do with the algorithm analysis. So we call it asymptotic algorithm analysis. So what does it mean? So asymptotic analysis of an algorithm, or we call it asymptotic algorithm analysis. We want to determine the running life in big O notation. So later in the code, you will do practice. So in the practice, I will ask you what is the algorithm analysis. So you need to write the big O notation. So how can you write the big O notation? So there are two ways. Okay? To perform the asymptotic analysis, first, find the worst case number of primitive operations. How can you do this one? We learn from the previous example. Okay, we calculate like this one. We calculate one by one. With one input, you check. Okay, this is two operation, two n operation, and so on. And then at the end, you need to express this function with big O notation. Now, you know that the find max function runs in ON. When you check the prefix operation, it shows that it is for n plus 5. This is the best case. And then it is 5n plus 5. This is the worst case. And at the end, you will just write it is ON. Because we know this is linear function. As we learned before, constant factors, lower order terms are eventually dropped. So you can just believe. So we can disregard them when we count the primitive operations. It means whenever you do this kind of analysis, you will just need the function. You will just need the 7 functions that you learned at the first time. The 7th function is the constant, log, the linear, and then n log n, and then quadratic, cubic, and exponential. So you need to only address with this function in the Pico. Now, let's see another example. I want to compute prefix averages. What does it mean by prefix averages? So the problem is, show the asymptotic analysis with 3 algorithms for prefix averages. So prefix averages, we got this one as the I prefix average of an array X is average of the first I plus 1 elements. We have this formula. AI will be equal to x0 plus x1 plus something until xi divided by I plus 1. So we want to compute the array A of prefix averages of another array X. This application is in the financial analysis. So, for example, let's say this is the array element. at the first element, maybe at the time point one. Okay, in the time point one, we have the element is 21. So the average is 21. And in the time element two, we have a value 21 and 23. So what is the average? 21 plus 23 divided by 2. And we have 22. At the time point 3, we have another value, which is 25. So what is the average? 21 plus 22, sorry, 23 plus 25 divided by 2. Then we get 23. At the time point 4, we have a new value, which is 31. Then what is the average? It is 21 plus 23 plus 25 plus 31 divided by 4. Then we get the average 25 and so on. So whenever we have a new value, we directly calculate the average. Now, with this example, how we can make the algorithm. So let's say I have this algorithm. This is the prefix average. I just mentioned this is algo 1 or this is the algorithm 1. The following algorithm computes the prefix average in the quadratic time. Okay, how do we know this is quadratic? Quadratic, what does it mean quadratic? This is n power of 2. Okay, so when you analyze the code, you will see this one. N equals to length s. So this is one operation. Okay, this is one operation. Okay, maybe you can say this is two operation. A equals to array 0 for n time. Then this is 1 and 1. This is two operation. A loop until n. So this will be n. This is one operation. So n until 1 until it is only one operation until n times. And then we have another 4. So this another 4, it is another n. So it means this will be n multiplied by n. And this will run for n multiplied by n time. This one will follow with this 4. So it is n time. Based on the rules, okay, we can say that just drop the constant and drop the lower order. So what is the constant? Yeah, this is constant. We can drop. And then you can see that in this case, the highest one is n multiplied by n. So this n power of 2. So what is the lower order? The lower order is n. Then we can just drop this one. So we say that this function is quadratic because we just look at the highest order. What about the algorithm 2? The algorithm 2, we try to solve the prefix average. Yeah, it says looks better. Maybe because this is looks simple or shorter. Okay. The previous example, oh, sorry, the previous example is like 10 rows. The algorithm 2 is 7 rows. So we can see this one with the running time. So the running time of the prefix average one is like this one, 1, 2 until n. And then because we want to do the summation, so there's the function n multiplied by n plus 1 divided by 2. So this is the n part of 2. So we solve from the line by line by the primitive operations in the algorithm. In this case, we can also check. This is 2 operation. This is 2 operation. This is n operation. Sum. What does it mean by sum? We want to do addition. S 0 dot j plus 1. It means we will do the summation from index 0 until j plus 1. So this is another function and it will take n time. So n when we do this one, it will take n times. Even though the code is shorter, but the operation is still the same. In the n operation, we still need to do another n. So this will be n multiplied by n. Because e multiplied by n, then this is still what? What about the algorithm tree? Now the algorithm tree is better because it is linear time. Okay, let's see. The following algorithm computes prefix averages in the linear time by keeping a random sum. So we have this method creation. This is two operation, one operation, but we will drop this one. So we don't care. It is constant. Now we need to check this one. And what about this? This is primitive operation. Primitive operation means we just calculate this one as the constant. Maybe this is, if you still remember, in the total plus equal means total plus sj. So in this case, we have only two operations, equal and plus, or maybe 3 with this indexing. So there are 3 operations. But this primitive operation, only primitive operation. This is primitive operation. And what about this? This is also assignment, indexing, and division. So this is also another primitive operation. So we have n. This is primitive operation. We can just drop constant. This is another primitive operation. This is also another constant operation. Then we can say this will be only n times. Then the prefix average tree will run for n. Okay, now which one is better? Algo 1. It runs n power of 2. Algo 2. It runs n power of 2. Algo 3. It runs n. Which one's better? Algo 1. Algo 2. Algo 3. Yes. Because it has the lowest function. Or because this is the complexity is linear. The lower function, the better. So if you can get a good algorithm, means the algorithm should pass should be fixed than the other algorithm. It means the function should be the lowest function. There are some relative of peak O. We call it peak omega and peak theta. So peak omega means Fn is omega Gn if there is constant C greater than 0 and integer constant n 0 greater than 1 such that it is function. So if you still remember the peak O, okay, with the peak O, we have Fn is smaller than equal to the C Gn. For peak omega, it is the Fn to be greater than or equal to C Gn. For peak theta, it should be like this one. So we have C prime. C prime is a constant and C double prime is another constant. So C prime of Gn, it will be in between of the Fn and the C double prime Gn. So we call this is peak theta. Just in the simple expression, we call it, if it is big O, so it is less than or equal to Gn. If it is big omega, it is greater than or equal to Gn. If it is big theta, then it is equal. Okay, so that's the simple definition about the asymptotic notation. So let's see. What is this? Is it true or false? N power 2 is big omega n power 2. True or false? This is yes. Omega means Fn is greater than or equal to the Cn. In this case, it is greater than or equal. Still equal. What about this? 5n power 2 is big omega n. Okay, this is also true because Fn should be greater than the Cgn. So Fn in this case n power of 2 and Gn it is n. So the function this one is greater than this Gn. What about this? Fn should be in between Gn with the C prime and C double prime Gn. It should be equal. Then n power of 2 is equal to this one. Then this is also 2. So this is also 2. Okay, this is just more for your practice. When you have this kind of Python code, then you can try to figure out. We can say this operation is O n power of 2. Right? You can check this operation. And as we know, this operation we can ignore. We can drop out because it is just a constant. And then we have n. So you can see there are 2 loops. If there are 2 loops, most probably it is n of 2. Because you will do this n times, you will do this n times, so then it means n multiplied by n. And this is constant for n multiplied by n. This form is with this one, then we have n for n types, and then the last one. The last one is only a simple equation. Then this is one equation. You can calculate like this one, but because sometimes you don't need this one. At the end, you just need the n power of 2. So we got this as O n power of 2. So if you do with the guru, you cannot write n power of 2 like this one. N 2. So it is not possible to write in guru. So when you do the practice, please write n at. Okay, so n at 2 means this is n exponent 2. In the guru, if you have this problem, then you need to write like this for n power of 2. Okay, we learn functions such as the constant, log, linear, and log n, quadratic, cubic, exponential, and you learn about the big O, big theta, and big omega. Any questions until now? So you can go to the Jupyter lab. So I show you the code. Okay. So for example, this is constant or just one operation. This operation, okay, just one operation, and then for this one, we will do for why 5 times, because we have the range until 5, and then this is a loop. So if it is n, then it depends on this number, and this is 5 times. So if I have another 4, so it means I have another 5 times. That's why n multiplied by 5. Okay. For the sum algorithm, yeah, I give you this sum algorithm. It is similar with the example in the PowerPoint, but this is only summation. But in the PowerPoint, we do the prefix average. Okay, in the prefix average, after we do the summation, we divide with the number of data. For the sum algorithm, we just do the summation. If we have 21 and 23, then we do the summation 21 plus 23, and so on. So you can check if I want to know how long does it take to solve this problem with small data and with the big data. Then you can run. So I will do a number until 10,000. So the time to finish this one is at this one. And then let's say, yeah, I have another kind of trial with different numbers. Then, so if the number is 10,000, then it will take like 0.02. If the number is 100,000, it will take this amount of time. If the number of data is 1 million, yeah, oh, this is 1 million, this is 10 million, 1K, then it will take about 1 second to solve the problem. Then you can see this one is n time, ON. Yeah, this is another example, so you can check. the code, and then you can try to figure out how to analyze this code. Okay, I will continue to the next section. So in this section, I would like to discuss about the algorithm design. So there are many kind of algorithm design. We have the recursion, divide and conquer, dynamic programming, greedy algorithm, and so on. So let's do the first one, which is recursion. So we will check the other parts in another section. So we will learn what is recursion, and then what is linear recursion, and what are the variants of recursion. In the class, I give you the source code, and so I give you the source code. You can check later the factorial, Fibonacci, power.py, list.py, and there are two codes. This is for the practice. So you can see later in the column. So what is recursion? Okay, we call the recursion. Recursion, it is a method that calls itself until a condition is fulfilled. So the core idea is to break down a problem into smaller, self-similar sub-problems. So the classical example, if you know loop function, okay, so the loop function is similar to the recursion. I want to print from 1 until 10, and we will just do with for loop. For I in prints plus is 1 until 11. Do you know why? 1 11. If I want to print from 1 until 10, it means I will do the code for I in range 1 colon 11. Let's see. Happen the recursion. So if I have for I in range 1 until 11, print I, comma n equals to length. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I hope that you understand this one. 1 is the starting number and 11 is the ending number. So we will print until n minus 1. Okay, so n minus 1 means 11 minus 1, which is 10. Now, we can do this one with recursion. So the recursive definition, we call it, this is Fn equals to Fn minus 1. Usually we will do down grade or count down. If we have I, we can do upper or we can do lower. If we do lower, then we can do like this one, count down I, print I, count down I minus 1. So count down I, let's say I give you 5. Then I will print 5 and then I minus 1. So 5 minus 1. It will be 4. Because this is countdown, then it means I will call again this function. Now countdown 4. I will print 4, and then again countdown I minus 1. Then it means countdown I, which is 1 minus 1. Now it becomes 3, and so on. So it will go down, 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 down. But using this function, it will be infinite loop. So infinite loop means the loop will goes and until no limit. So in the recursion, we have base. A Python method with base. It means I need to have a something criteria. When you have the countdown n, I want to print. This is the base. If n less than or equal to 1, or bigger. If not, then countdown n minus 1. So countdown n minus 1 means I will do again this function. So the formula will be something like this. Fn, it will be Fn minus 1 if it is else. If n is less than 1, it is empty. Okay, one more time. If it is less than 1, it is empty. Otherwise, go to n minus 1. Because this is the recursive method. The recursive method or the recursion usually is the same. We have base case. So the values of the input variables for which we perform no recursive calls are called base cases. So there should be at least one base case. Every possible chain of recursive calls must eventually reach the base case. And we have the recursive calls. It means we will call the current method. And its recursive calls should be defined so that it makes progress toward the base case. So we should go to the base case. Now let's see. Do you know factorial? 5 factorial. What is it? It's 5 multiplied by 4, multiplied by 3, multiplied by 2, and then multiplied by 1. This is the 5 factorial. In the definition, then I have a function. It will be n multiplied by fn minus 1. So it will be 5 multiplied minus 1. And then this one, it will be multiplied by minus 1. This will be multiplied by minus 1. This will be multiplied by minus 1. But when n equals to 0, that makes it 1. So some factorial like this one. And if n equals to 0, then it will be 1. This is the base case. If not, then let's calculate this function. So let's see. This is factorial. Factorial n equals to 0. It will return 1 if it is 0. If not, then let's do the multiplication. So the factorial 5 is 120. 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. And this is 120. So the idea of this is, this recursion. So this recursion means if I have a number, Each box represents the recursive call. An arrow from each column to the colony, and an arrow from each colony to column showing the return value. Now I have the recursive factorial form. It will check 4 equals to 0. 4 equals to 0. No. Then we go calling 3. It becomes 3. 3 equals to 0. No. It goes 2. 2 equals to 0. No. 1 equals to 0. No. 0 equals to 0. Yes. Because it is yes, then it returns 1. And after we got 1, we will multiply with the upper side. So we return back. So 1 multiplied by 1, we get 1. And then we return back to the 2. 2 multiplied by 1, we get 2. And then again, we return back to 3. 3 multiplied by 2, we got 6. And then we return back to 4. 4 multiplied by 6, we got 24. So that's the final answer with the recursion. Right? Mm-hmm. It's just an orbit, right? Yeah. Suspense. What happened? This is okay. Okay. What happened? Okay. The PowerPoint is finished. Mhm. Okay, anyway, this is suspense. I cannot move the mouse. I cannot move the PowerPoint. Okay, then I will stop here because you need to do the learning check.